Thanks for watching my presentation. This is Chris Tae-yoon Kim from South Korea, who is earning PhD under Professor Tirapap Chareon-Bilyapap at Kasetsat University in Bangkok, Thailand. Today, I would like to talk about one of my research topics, chemical lure development using high-throughput screening system for Aedes aegypti surveillance tools. Let me start. Dengue is one of the major problems in tropical area. It increased 30 times for last 50 years, and now the cases are about 100 million per year. 4 billion people in 141 countries are exposed to dengue risk, but 75% are in Asia-Pacific region. Entomological surveillance tools like traps and lure provide vital information to manage the vector-borne disease. The two major dengue vectors are Aedes aegypti and Aedes albopictus. To increase catching rates, chemical lures were developed using various types of olfactometer to see lure preferences. However, complicated olfactometer settings using airflows, for example, may cause limited lure developmental access for less sophisticated laboratories. In addition, biogeographically different local mosquito populations may respond indifferently to the imported lure product. In this study, we provided a methodology for testing lure candidates using the HITSS and semi-field greenhouse assay. However, as the HITSS assay originally designed for the repellent, we had to evaluate for the attractant. For that, we optimized one of the best lure products, BG lure, using the HITSS assay. After that, we screened 6 different lure candidates we've made to select the best one. In addition, we compared the percent attraction of each lab strain and field population to see any differences in host-seeking behavior. The pictures on the screen describe the HITSS assay. Basically, it consists of 3 parts. From the left, untreated chamber, middle chamber, and lure-treated chamber. The cylinders connected using a disc, which has a butterfly door. 20 non-blood-fed females were introduced in the middle chamber. Immediately, we covered it using a dark felt to avoid any influences from the light. 30 seconds later, both sides of the butterfly doors were opened. After 10 minutes, the doors were closed and counted the number of mosquitoes in each chamber. For the optimizing assay, we started with a pack of BG lure, which is 10 grams, but it strongly repelled the mosquitoes, so that we tested 10 different amounts by decreasing the amount up to 0.005 grams. For the screening assay, we selected a discriminating dose for all 6 different lure candidates. The KU lures were mixed by one of my co-supervisors, Dr. Tirapap Chareon-Bilyapap from Department of Chemistry at Kasetsat University. As followed the same protocol with the BG lure optimizing assay, we calculated percent attraction using a formula provided on the screen. 9 replicates were conducted for each treatment, and both parasitoid susceptible and resistant mosquitoes were compared. Let's look at the result. The bar graphs on the screen shows the result from each assay between lab and field population. The y-axis is percent attraction. Positive means attracted, negative means repelled. Please look at the graph on the left side. The numbers in x-axis are the amount of BG lure tested. As we can see in the red box, the BG lure was attractive in between 0.005 gram to 0.1 gram. However, the mosquitoes were repelled by higher amounts of the BG lures in HITSS assay. From this result, we selected a discriminating dose, 0.01 gram, for the KU lure screening assay on your right-hand side. The percent attraction for each KU lure candidate described, and the most females were attracted to only the KU lure number 1 compared to other candidates. Overall, there was no significantly different responses between the field and lab strains. To sum up, the HITSS assay successfully optimized the BG lure and also selected the best KU lure candidate. However, as this result still needs to be confirmed in a large scale. So we took all the things to the semi-field screenhouse assay located 200 kilometers away from Bangkok during pandemic last year. Here is the facilities for the semi-field screenhouse assay. We followed the HITSS assay protocol and tested Aedes aegypti field population only. In the screenhouse assay, we used the 2 BG sentinel traps, and one for untreated, the other one for lure treated. Both traps were placed 10 meters apart from each other, and 50 non-blood-fed females were introduced in the middle at 6 in the morning. We collected the captured mosquitoes from each trap hourly till 6 in the evening. Temperature and humidity also recorded, and conducted 8 replicates for each treatment. The first assay was optimizing. To select a discriminating dose for the semi-field screenhouse assay, we optimized the KU lure number 1 by testing 5 different amounts in the assay. And next, we screened the 6 different KU lure candidates using the single dose, 0.5 gram from the optimizing assay. And also, we put positive controls, one for the BG lure, the other one for carbon dioxide singly. This is the result for the optimizing and screening assay in the larger scale semi-field screenhouse assay. Basically, as I highlighted in yellow, the BG sentinel trap itself without lure could recapture over 90% of the mosquitoes, and there was no significant difference with lure or carbon dioxide treated one. However, the number of mosquitoes recaptured in each side of traps were that the both untreated for the control were not significantly different. For the optimizing assay, 1.0 gram to 2.0 gram of KU lure number 1 treated BG sentinel traps showed negative value for the percent attraction, but it turns to the positive with the smaller amount. We selected 0.5 gram from the optimizing assay as a discriminating dose for the screening assay. Please see the KU lure number 1 in the red box. The number of mosquitoes recaptured in treated trap was significantly more than untreated trap. Furthermore, the percent attraction is positive only for this lure. Surprisingly, the percent attraction was not significantly different with carbon dioxide treated trap. In contrast, 10 gram of BG lure treated trap was significantly less compared to both KU lure number 1 and HITSS carbon dioxide treated traps. In conclusion, first, we proved accuracy of the HITSS assay result in the semi-field screenhouse assay. Second, the HITSS assay successfully optimized the BG lure, and the result showed dose-dependent reversal responses that higher doses repelled while the lower dose attracted, which is very common. In addition, using the selected discriminating dose, the HITSS assay could screen meaningful lure candidates from the multiple mixtures. Lastly, there was no significantly different lure preference between pesticide-resistant local population and laboratory susceptible strain. This is what I have prepared for today. I would like to thank to my funding sources, Thailand Research Fund and Graduate School of the Kasesa University. Also thanks to National Institute of Health for providing us the HITSS devices. Finally, thanks for your attention, and please send me an email with your invaluable comments on this study to my email address, dayun.k@ku.th.